Talk about an important problem with page tables, which is size, and then talk about a solution which we're going to refer to as multi-level page tables or hierarchical page tables. What's the problem? Let's take an example to understand what the problem is. So let's assume a 64-bit ISA and the page size is 4 kilobytes. The maximum number of virtual pages you would have in a 64-bit ISA is 2 to the power of 64 bytes divided by the page size, which is 4 kilobytes. So 64 minus 2 to the power of 12, that's 12 bits. So 64 minus 12, that is 52. So totally we have 2 to the power 52 virtual pages. That's a lot of virtual pages. And we also said in the case of a page table, we are going to have an entry for every single virtual page. So if you have 2 to the power of 52 virtual pages, then we have 2 to the power of 52 page table entries. And now let's assume for the argument's sake that the page table entry size is 4 bytes. Typically this would be your size of your physical page number with the valid bit and other metadata that we talked about earlier. Let's, for the argument's sake, assume it's 4 bytes. So now to understand how big of a page table we need to multiply the number of entries by the size of each entry. So that would give us 2 to the power 54 bytes. Now that's a lot of space. Now that's to put that in some perspective, we need about 160,000 DRAMs, each of size 100 gigabytes. So now even if you take all the DRAMs that we have in all the computers at University of Michigan, that still won't be enough, most likely, right? So clearly this is not a feasible solution. We need to find ways to try and reduce the size of page table that we need. How do we do that? Well, let's think about an idea that we have used to reduce the physical space that we need for the virtual memory. So the main trick that the operating system uses is, like I said before, on-demand paging. What that means is when the process starts, the operating system does not allocate physical pages for all the virtual memory. It allocates a small fraction for the instructions on the data segment, and as the program executes, more and more physical pages are allocated to that process, right? And so can we use a similar idea for page table as well? When we talked about page table, we said when we start off the process, we will create this page table, and that page table will have one entry for every virtual page. That's what we said. That turned out to be a bad idea because it needs too much space. So now what we are going to try and do is, instead of allocating 2 to the power of 54 bytes worth of page table right when a 64-bit program starts, we're not going to do that. Instead, we are going to try and allocate the space on demand as and when a program needs more pages for its data. So the idea of on-demand paging, we are going to not only apply it for data pages, but we are going to try and apply it for page tables that maintain that translation as well. But we cannot just directly apply it because we need to always have the capability to translate every single virtual address, right? We cannot afford to say, well, I'm just not going to keep track of any information for a virtual address. That's just not possible. We need to have some information, the translation information for every virtual address. So we can't skip that role. So let's see how to go about doing that. Now, I want to go through this exercise of understanding the size of page tables for 2 different page sizes. And maybe that will help us understand how we may go about solving this problem. On the left side, you have an example for page of size 4 kilobytes. And on the right side, you have a page of size 16 kilobytes, 4 times larger. Now let's see how this page table size affects the page table size. Okay, so now if you just understand how page size affects the page offset, we went through that before. Log to the base 2 of 4 kilo, that is 12 bits. And that means that the remaining becomes your virtual page number. In this example, I'm assuming a 20-bit architecture, so 20 minus 12, that's 8 bits. And so that gives us a total of 256 virtual pages. Now that means for the design that we spoke about before, we need 256 entries in the page table. Now let me assume that my page table holds just the physical page number for the moment. I'm ignoring all the metadata. Now let's compute how big this physical page number would be. So that would be everything minus the page offset size. I'm just going to simply assume that my physical memory size is 2 to the power of 18. So 18 minus 12 bits, that gives me 6 bits. Now your main memory size could be larger, smaller. That doesn't matter for this particular point I want to make. Let's assume that it is 2 to the power of 18 bytes. All right, so the most important takeaway for this example is there are 256 virtual pages and I need one entry for each one of them. Now let's increase the page size from 4 kilobytes to 16 kilobytes and let's see what happens. So now my page offset would increase from 12 bits to 14 bits, 13 plus 1 because I'm starting from 0. So 14 bits. So I have 2 more bits that goes towards page offset, which means that my virtual page number reduces from 8 bits to 6 bits, which basically means that my number of virtual pages reduces to 64 pages. A simpler way to think about it is I had 256 pages before, but now I have multiplied the page size by 4. So that means I need to divide the number of pages I had by 4. So 256 by 4 would get me to 64 pages. So imagine I had 256 pages, each of size 4 kilobytes. When I increase the size of each page by 4 times, I would reduce the number of pages by 4 times. So now I have fewer pages. Keep in mind that the virtual memory size is still the same. I just increased the granularity of pages. That's all I did. And so now I have fewer pages, but each of them is bigger than before. So in this example, now I have 64 pages. Now what that means is my page table now only needs 64 entries, right? Now before I had 256 entry page table, but now I need only 64 entries. Now does it mean each entry would increase proportionately? No. Each entry still has a physical page number. So if you do the math, your page offset increased by 2 bits. So in fact, if I keep my physical memory size the same as before, I went from a 6-bit physical page number to a 4-bit physical page number. So in fact, my page table entry size also reduced. It's not a significant reduction. We got 4x reduction for the number of entries, and we got a pretty modest reduction for the page table entry size. So if you put those two things together, you will see that before I needed 256 entries, each of size 6 bits. Together I have 1536 bits. Now I have 1/4 the number of pages as before, so that's 64, and each of them has to hold only a smaller page number, physical page number, so together I have 256 bits. So roughly, when I increased my page size by 4 times, I decreased my page table size by 4 times. So the takeaway here is that the larger the page size, smaller the page table. Okay, now the question is, if I'm worried about the page table size, can I just solve the problem by simply increasing the page size to as much as I want? The answer is you could do that up to a point, but after a point, let's say 16 kilobytes or 128 kilobytes even, you are going to run into fragmentation issues. What I mean by that is when a program accesses any address, operating system is obligated to allocate an entire page containing that address. So if I access one address in a page that doesn't exist in main memory, now I have to bring in the whole page and allocate it in main memory. Now that's probably okay if you have small pages like 4 kilobytes, but once I'm talking about, let's say, 128 kilobytes, right, that's going to be a problem, because maybe the program is not going to access all parts of that page. And if it doesn't, then I'm going to waste my main memory space. So larger pages can result in poor utilization of main memory. So that's not a good idea, right? So let's say I want to keep my page size to be small, to be 4 kilobytes, but I still want to get this benefit that I have with these large pages. So can I get the best of both worlds, where I have smaller pages, but I have page tables that are only as large as I need it to be for super pages, let's say 16 kilobytes, like we discussed in our example. Well, we can't exactly get the best of both worlds, but we can get pretty close by leveraging, again, the idea of on-demand allocation. Let's see how that works. Well, I'm going to complicate this example a little bit more, and I hope you're not going to get lost. So what I have now is the same construction as before on the left hand side. So page size is still 4 kilobytes, because we said I love small pages because it has less fragmentation. So I'm going to keep it 4 kilobytes, which means that everything else remains the same. So my virtual page number remains to be 8 bits, which means my number of virtual pages is same as before, which is 256 pages. Now normally I would need a page table with 256 entries, and we said for this example it's probably okay, but we went through an example for 64-bit architecture for 4 kilobyte pages, and that ended up being too big, right? So we want to reduce this page table size. We don't want to always allocate 256 entries, because if I do for a real program, I wouldn't have enough space to store it. Okay, now on the right hand side is what is new. What I have done is, remember when I talked about 16 kilobytes, I said my page offset is going to be 14 bits, and therefore my virtual page number is only 6 bits. I'm going to keep this 6 bits as before. So this orange field that you see is the index for a page table if I had a super page of size 16 kilobytes, right? The same math that we did holds true. But I'm going to go back to my original page offset, which is 12 bits, because I want to have small pages. So I'm going to go back to my original page offset of 12 bits. So I'm keeping my super page field, and I'm keeping my smaller page offset. Now I'm still left with these 2 extra bits in the middle. Okay, so the main idea is the following. I'm going to have a super page table that manages as if my pages are super pages. So what that means is, if my pages are super pages of size 16 kilobytes, then I would need only 64 entries for such a page table. And the index into this page table would be derived from these 6 bits of the virtual address. Now I can index into this table and retrieve an address translation. Now if that address translation directly points to a physical memory location for a super page, I will be done at this point, but my page sizes will be super page. I don't want that. I want smaller page. So what do? Well, this entry is going to hold not the base address of the super page. Instead, it's going to hold the base address of a second level page table. What is the second level page table? The second level page table is essentially what I originally had, except that now I have broken that page table into much smaller chunks, each of size 4 entries. So this address is going to point to a second level page table with 4 entries, where each entry is going to hold the physical page number of a smaller page of size 4 kilobytes. Okay, so if I have 4 entries in this table, 1, 2, 3, 4, each of them corresponds to a smaller page of size 4 kilobytes. So if I aggregate them all, I would get 16 kilobytes. So now you can see how this entry here corresponds to a super page of size 16 kilobytes, but I'm not directly translating its address to a physical address. Instead, I'm going through another level of indirection, and this another level of indirection table here helps me translate that 16 kilobytes, breaks that into 4 kilobytes each, and gives me an address for each 4 kilobyte page within that super page. Now you may ask, okay, now it doesn't seem like I did anything better, because now I need this original table, plus I have added this one more table. So how does this help me save any space at all? It sounds like I need more space than before. Well, that may be true, but here is a trick. When I start my process, I don't need to allocate space for this table at all. I only need to allocate space for this table over here, the first level table, which covers all of my virtual addresses from 0 to 2 to the power of 20. It covers all my addresses, but it's going to do the translation at the granularity of a super page, so therefore I need only 64 entries. As and when my program accesses data from pages that have not yet been allocated, the operating system is going to allocate pages, but it's going to allocate pages at the granularity of 4 kilobytes. So what it does is, let's say that the super page 0 has not yet been allocated. So what I will do, the operating system will do is, this has never been allocated before. So now the first thing I'm going to do is to create a second level page table for it. So this table, remember, was not allocated at the beginning of the program. I allocated only this table. And so the first time any page within the super page is accessed, only then the second level page is allocated. So second level page table is allocated. And that page table will obviously have 4 entries in them. And then let's say the store or load had accessed, let's say, the physical page number 0. And so in that case, the operating system was going to only allocate the physical page for one small 4 kilobyte page, and the rest of these guys is going to be set to invalid. So now I have 2 level indirection. So whenever I need to look up an address, I'm going to look into this super page table, retrieve the address of my second level page table, and the second level page table is going to tell me the actual physical address for the page I'm looking for. Now the way that these things work is I've broken down this virtual address into 3 fields: first level, second level, and the page offset. You must be already familiar with page offset, so I'm going to leave that out of the discussion, which is 4 kilobytes that we are assuming, so 12 bits. And then the remaining is what we usually call it as a virtual page number. So that used to index into a single level page table, but now we're going to say I'm going to leave out these 2 bits, and rather I'm going to treat that as a super page. So super page, if let's say is 4 times larger than your actual page, so then you need 2 bits here. Let's say if it is 8 times larger than your actual page, so this will be 3 bits instead of 2 bits. If it is 16 times larger than my actual page, this will have 4 bits, and the remaining is what would be the first level. The first level table, think of it as a super page table that manages the translation for super pages, the big pages. Now they don't actually contain the actual address for a physical memory location that contains the superpage. No. Instead, it contains the physical page address that allows the operating system to retrieve the second level page table, which then contains the individual translations for all the small pages within that superpage. And the way I would index into this second level table is by using the remaining bits in between my first level and the page offset. So in this case it will be 2 bits because my super page has 4 smaller pages, so I need 2 bits to select from one of those 4 entries. And once I have identified the entry, then I get my physical page number, and then I plug it in here, and then I get my physical address, and then I go and access my physical memory. Hierarchical page tables is a little bit of a challenging topic, so I'm going to explain it in a different way and see if hopefully that helps as well. So I have the same example that I just went through, but I'm going to try and articulate how we are able to save space. So again, I have broken down the virtual address into 3 parts. The orange part corresponds to the super page, the green part corresponds to the smaller pages. And the page offset, we don't care about it in address translation. Now, when the program starts, the operating system allocates a super page table that contains as many entries as the number of super pages in virtual memory. In this example, it would be 2 to the power of 6 virtual super pages. So because I have 2 to the power of 6 virtual super pages, I need 2 to the power of 6 page table entry in my super page table. So the number of entries here will be from 0 till 63. So I need 6 bits in to address it, so I'm going to use my 6 higher order bits to index into this table. Now the the page table entry in the super page table contains an address that refers to a second level page table. So how many second level page tables do I have? Let's stop here and you think about it. So I have 64 page table entries in my super page table, and I said each one of them refers to a second level page table. So clearly I must have 64 second level page tables. So I'm going to create 64 second level page tables. These will be much more smaller. Obviously I don't have space for 64 boxes, so I'm just going to stop here. And how many entries should these second level page tables contain? Well, we said each super page is of size 16 kilobytes, and each super page is composed of 4 smaller pages, each of size 4 kilobytes. And what we are really trying to figure out is, given a super page, we want to translate the addresses of each of its individual small pages. So from my super page table, I get the address of my second level page table, and then my second level page table should hold the address translations for 4 of the small pages that are contained within that 16 kilobyte super page. So each second level page table should have 4 entries in this example. Okay, and like we said, we have 64 of these second level page tables. We have only one of this super page table. Now the way that I would select one of these 64 page tables is through the address here, right? So the address that you get from the super page table is the one that will be used to access one of these second level page tables. Okay, and in order to figure out which entry that you should get from your second level page table, I would use these 2 bits for that. So there are 4 entries in your second level page table, and I can use the 2 bits from my virtual address to select my small page within that super page. Okay, so now let me summarize the discussion that we just had about hierarchical page tables. What we discussed so far is two-level page table, and it is, think of it like a tree-like structure where the first level page table is the root, and it contains the address to the second level page table. So you can think of the first level super page table to be the root set of root pointers, and these to be the leaves, right? So this is the root and these are the leaves in a hierarchical structure. And the second level page table is same as the entry in the single level page table. Second level page table is same as an entry in the single level page table. So what that means is that if I concatenate all of these 64 second level page tables together, so that will be 64 times 4, that is 256, what I would get is the original single level page table. So another way to think about it is that I took my original single level page table and I split it into 64 smaller tables, and I got these. And the reason why this method is more space efficient than just having one single level page table is because of the following reason. When a process starts, I'm only going to allocate the first level page table. Okay, what that means is only this page table is going to be allocated, only the super page table is going to be allocated, and that has only 64 entries as opposed to the 256 entries that we had in the single level page table. So it's 4 times smaller, right? Remember, the super page is 4 times bigger, so I'm able to shrink the super page table by 4 times compared to the single level page table, and that is what I need to allocate when the process starts, and that's why my space is much lower in requirement. And as the program executes, that's when one of these 64 second level page tables will be allocated. So these second level page tables are going to be allocated on demand when the program executes. And the hope is that your program never really gets to access all of the address space, and so if it doesn't really access all of the address space, then I can get away by just allocating a subset of these 64 second level page tables. And so I could take this idea and then generalize it to n level page tables. So in this example, we just considered 2 levels, but I could keep this going, right? In fact, in modern systems, they use 3 levels at least, especially for a 64-bit architecture. Even 2 levels are not enough, because your super page tables are too large, and so you don't want that. So you want your super page table, the first level that you're allocating, to be very small, because you're always going to allocate the first level when a process starts, and you want that to be as small as possible. To do that, you need to have multiple levels, not just 2. The benefits are similar. Okay, so here is another way to visualize the construction here. So I have divided my virtual address into these 3 parts. The way that your operating system would do the address translation is by first taking the first level index it into the super page table, get the address of the second level page table, and then go and retrieve the second level page table. And to figure out which entry in the second level page table you must access, you need to add the base address to the second level index. So that gives you the effective address into the second level page table. And if your multi-level page table has only 2 levels, the second level page table should have the physical page number of the virtual page number that you're trying to translate. You retrieve that, and then you concatenate that with the page offset, you get your physical address. So why do we get space benefits? It is because of on-demand allocation of the second level page table. The second level page table size is proportional to the amount of virtual memory that is used by the process. So if your process accesses only a subset of the virtual memory, then the amount of page table size occupied will be proportional to that, right? And so in the common case, the hope is that the size of the multi-level page table is much smaller than the single level, because you would have allocated only a very few second level page table. But in the worst case, you may need all the second level page table plus your super page table. So that may be, so remember, if I aggregate all the second level page tables, that would be the same number of entries that I had in the single level page table. So in the worst case, I need all the second level page tables, which basically means I would have all the single level page table entries plus the first level page table. So in fact, in the worst case, my multi-level page table would consume more space than the single level page table, because my first level page table is purely an overhead at that point. So how do I compare a single level with multi-level page table? With the single level, there is an advantage, which is that I need only one page table lookup to look up into the single level page table to do an address translation. But in the case of a multi-level page table, unfortunately, I need to do multiple lookups. So if I have a 2-level page table, I need to do 2 lookups. If I have n level page table, I need to do n lookups. So the number of lookups increases with the number of levels, and that's bad because these page tables are stored in memory, so you're increasing the number of memory accesses when you increase the number of levels, and so that's a trade-off. But the advantage of the multi-level page table is, of course, that you're allocating page tables on demand. So in the common case, when your program uses much less virtual memory, then the total amount of page table size would be much less than single level, which is obviously a downside for your single level page table, because all the page table entries are allocated at the beginning of the program, and obviously that is not good, because like we talked about, for a 64-bit architecture, it would be prohibitive to allocate the entire page table for a 64-bit program at the beginning of the execution.